Hello, everybody. This video is on a course at UNSW called Maths2099. But this is a general fact. Some other people can use it pretty well as well. So I would like to explain coordinate vectors in the first place. Then I would like to explain how the matrix form of a linear transformation we can form with respect to a basis, and how we can move from one basis to another basis with respect to the just the matrix forms of the linear transformation with respect to the basis, to different bases. This is to try to understand first what is the coordinate vectors means. That's what would like to start with. If that is clear, then the working on the matrix form of a linear transformation with respect to a basis, which will be much more clear. Okay, now S, this curly S is E1, E2, E3, and this is a standard basis of R3. You can extend to this idea for other things, but I would like to focus on the question 34 and explain the general ideas behind it. Okay, we know that standard basis E1, E2, E3 of this kind. And why we have a basis of why we are dealing with the basis of a vector space is basically every vector can be written as a linear combination uniquely of the basis vector. So this is the key idea why we are working in the basis. So if you have a vector, say with components x1, x2, x3, then we can write this vector as x1, e1, x2, e2, x3, e3, right? This is a linear combination, and the coefficients will be x1, x2, x3, which corresponds to coordinates of the vector, right? So we call x1, x2, x3 is the coordinate vector with respect to the standard basis. Since standard basis is so obvious, so itself is the coordinate vector. Assume now we have a different basis. Assume we have vector v1, v2, v3 are given by in this question in this way. These are the same vectors in the question 34. And the set of these vectors is a basis for R3. This is given to us. We don't need to prove that. So what it means, since it is a basis, every vector can be written uniquely as a linear combination of the basis vectors. So X can be written as alpha V1, beta V2, gamma V3. We don't know alpha, beta, gamma, for example, but you will figure out by just solving this kind of equations, and that will give you the coordinate vector with respect to the basis B. Right? These are the coefficients, and these coefficients will be the coordinate vectors. So let's think that way. So X basically multiplications, think about that this is a matrix. This matrix consists of the column 1 is V1, column 2, V2, column 3, V3. And if you multiply this vector with this column, you will obtain this equality. This is just a matrix multiplication, right? This equality, this equation here is equivalent to the matrix multiplication form in this way. So call this one Q. So Q times X, alpha, beta, gamma gives you X. Since V1, V2, V3 are linearly independent vectors, the matrix that you are constructing here as Q will have an inverse because the columns are linearly independent. So the determinant will be non-zero. If you have a non-zero determinant of a matrix, then it has an inverse. Then we have a Q inverse. So if you multiply from this side by Q inverse, then you will have Q inverse, that will be identity. Then you will get alpha, beta, gamma. In this way, you will be able to get Q inverse X. Alpha, beta, gamma is the coordinate vector of X with respect to the basis B. Let's do a little example for the coordinate vector. So 2 minus 3, 0, for example. will be the sum of these three vectors. So all the coefficients is 1. So the coordinate vector of this vector with respect to the b will be these coefficients, which is just 1, 1, 1. And the coordinate vector of this vector with respect to standard basis is itself. If you have, so the vector, so I'm changed the order because in the questions, they want us to focus on the order V3, V2, V1, but it doesn't matter. So I constructed this Q matrix is V3, V2, V1 to be consistent with the question that I'm going to solve. So the order, once you choose the order, you need to keep that order in the whole question. So that was the question 34 all about as well. But so in this case, once I choose V3, V2, V1, I will keep going to that order throughout this question. That's my point. So this is V3, V1, V2. So that's the Q matrix. And we think about the any vector in R3. If you multiply this by x, then we will have some vector E3, which means that we can multiply this. It's exactly the same. So it's exactly the same idea as I am doing here with the numbers in this time, right? So just I would like to, this row here is remind you how to calculate the inverse. So you just write QI and you apply the row operations. And the left-hand side will be identity, and the right-hand side, that's the matrix that you're going to obtain, will be the Q inverse. So this line here are just recalling us how to calculate the Q inverse. So this is the Q inverse of the matrix Q, which is that one. So this is the in that order. So what I'm trying to say is that basically what we have on the above is 2 minus 3, 0 is the coordinate vector with respect to the standard basis. 1, 1, 1 is the coordinate vector with the same vector with respect to the basis B. They are exactly the same vectors, but the representation with respect to the different bases has different form, just a linear combination. So by just this Q and Q inverse, how it affects. So Q inverse takes the coordinate vector with respect to S to the coordinate vector with respect to B. And Q times this one, 1, 1, 1. So when we multiply Q, the coordinate vector with respect to the B will give us the coordinate vector with respect to the S. This is what we obtained from this example. Right? It is easy to see if you looked at this and multiply with this vector, right? Q inverse times this, for example. Let's focus on this one. So this row with this column will be 2 minus 3, 0. 2 minus 2 times 2 is 4. 4 minus 3 is 1. So this component is 1. So this row with this column will have 2 times 2 is 4 and minus 3, and that's 0. So this is 4 minus 3, it's 1. The last row, we will have minus 2. This times this, you will have minus 2 plus 3. That will give us 1 again. So as you realize, when we multiply Q inverse with this vector, we will obtain 1, 1, 1. This is the coordinate vector with respect to the S, and this is the coordinate vector with respect to the B. As is a standard basis, that's the another basis that we picked up. So as you see, the constructing Q and Q inverses makes us move from one basis to another basis. This idea, we are going to use this idea to calculate, to compute matrix form of a linear transformation with respect to the different bases. Now we consider two bases, S and B, which are given. And the question, this is question 24, and this is the T transformation from R3 to R3 and defined in this way. 5V1 is equal to 5V1 plus V2. TV2 is defined as 5V2 plus V3, and TV3 is defined as 5V3. And the order of the bases of this vector in this questions is chosen as V3, V2, V1. This is given in the question, so we are working out with this way. And the matrix form of T, it's easy to calculate. And this will be this matrix. Why? Because if you, so this order, the order is chosen for us in the question. So that's V3, V2, V1. So this equation here, TV3 is equal to, so this is TV3. TV3 is equal to 5V3. This is 5V3. And then TV2 is V3 plus 5V2. And V1, TV1 is equal to 5V1 plus V2, which is this guy. So this vector can be written as V3, V2, V1 times this matrix, because when I multiply this row with this column, I need to obtain this quantity. I can do only if I have 5, 0, 0, right? This times this times this times this should be 5V3. So I'm just figuring out, I'm writing down this matrix by myself. So I have these equations, I have these equations. So I have this vector and I have some matrix which will take me from this vector to this vector. Given by these equations, I'm figuring out this matrix by just thinking about the matrix multiplication. So this times this will be this one. So this row with this column will be V3 plus V2, 5V2, which is this one. And this times this will give me the 5V1, V2. So V1 is the last one. So this should be 5. This should be 1. And there's no V3 in the here. So this should be 0. So the first component 0, second component is John, last one is 5. I think this part is clear. We've done this before. But what we are having here, this matrix is the matrix form for this linear transformation T with respect to the basis B with order V3, V2, V1. Okay, now we would like to find out the matrix form for T with respect to the standard basis. So this is our task. Right? We want to find out matrix form of T with respect to the standard basis. Now, what we figured out, just up. If we multiply the vector in R3 by Q, that means we are moving from the basis B to the basis S. If we multiply a vector from R3 by Q inverse from the left, we are moving from the basis S to the basis B. This is what we realized up. So this blue and yellow parts, this is what we figured out in the first part of this video. I just would like to show you again, right? If I multiply a vector with the Q inverse from the left, I will obtain the coordinate vector with respect to the B. Right? If I multiply the vector given in the coordinate vector in B, and then I multiply by Q, then I will obtain the coordinate vector with respect to S. So Q moves from the basis B to S, right? So this is what I'm saying here. Q, multiplication by Q, I am moving from the basis B to the basis S. So what is this diagram is saying to me? This diagram is saying that we have a linear transformation T, which we can define as linear transformation from R3 to R3 as if moving from the standard basis of S to the standard basis of S. So we are looking at this R3 as a spanning set, as a basis of this vector space is S, the basis of this vector space S. We view it that way, and then we are looking at the matrix moving from here to here. But the same transformation we can define from another basis, because R3 has another basis B. From basis B to the basis B, we have another linear transformation, and we denote this matrix transformation by T subscript B. Right? We calculate this one just before, right? This is what we calculated. This is the linear transformation of, this is a matrix form of the linear transformation T with respect to the basis B. It's given to us. That's be calculated, be computed. Now our aim is to find out this yellow highlighted place. And we figured out we can move from the basis B to S by Q, from S to B by Q inverse. So we want to find out from this row to this row, right? I've tried to explain here much more clearly. So these are what we have. So this is the road that we would like to do. This question mark, this is what we would like to find out. I can reach this question mark with this way. So I will go down, I will go right, I will go up. Will be equivalent to go right. It's exactly the same thing. And this diagram is given as a commutative diagram. So first, I would like to go down because this is the domain for us. This is the domain for this matrix form. So from this domain, we are moving. From here to here, I'm moving from the span the basis S to the basis B. Now from here to here, I'm moving from the linear transformation with respect to the basis B. And from here to here, I'm moving from the basis B to the basis S again. But this diagram needs to be told as a function. So this road is not like a this road, this road, this road. So this one first, this one second, this one last. It's like a functions, composite of the functions, because exactly this is what's happening. These are the composite of the functions. So this question mark is the matrix form with respect to standard basis. First, apply the Q inverse. We are down. And then apply the transformation with respect to the basis B, which is that guy. And then go up again, which is Q. So this equation represents this green path. Once we write it down, this equation, it is simple to calculate, just a calculation. So this is the matrix form with respect to the B. This is Q and this is Q inverse. We need to multiply these three matrices. It's just a simple it's just a calculations, and you know how to calculate it. You just multiply these three matrices and you will end up being this matrix. Yeah, hopefully this will help. Hopefully it will clear up these graphs and how we do these calculations, how we think these calculations. That's all for this question. Thank you very much for listening. See you next time.